Good day, chemistry critters. Really did not expect to be making one of these today. I thought surely we would make the school today, but here we are. I imagine I'll be making another one tomorrow and hopefully seeing you guys on Monday. So with that in mind, I want to spare you guys the lecture one today, give you just some free response problems, some ones that I've doctored up from AP things to sort of reflect what we're doing. Mostly gas laws, but mixing in stoichiometry and intermolecular forces to keep you guys on your toes, because we need it, especially with the IMFs and stoichiometry. So I've posted a PDF version of this file on the high school's website for like my teacher page. So if you want to download it, you can navigate over to WestJess homepage, find the teacher page thing over there on the left and go to this, and I've got it posted up there. Otherwise, you can just read it off the screen, pause the video, get the numbers from the screen, whatever you want to do. I want to go over the problems, give you guys some pointers on what exactly to do, the things that you need to find, and just leave it to you guys to post any comments if you've got any questions. So let's go to it. First thing here, I don't know if you guys know this kind of story in the news, so I made a problem about it. Over in California, there's a storage facility for natural gas called Aliso Canyon, and it is currently massively leaking natural gas. We're talking when the leak first started, 44,000 kilograms of it coming out of here an hour. It's pretty crazy. Basically, what they've done is they need to store natural gas kind of in the off season, so it's ready when they need it. So they pump it back into old depleted natural gas wells. Kind of ironic that we take natural gas out of the ground and then we put it right back in there. Anyway, they use that as a storage facility for the population living in Los Angeles. So the storage facility contains approximately 22 billion cubic feet of natural gas. There we are in liters for use in PervNert. It's confined deep underground in these old wells. The pressure underground would be approximately 20 atmospheres, and it's deep enough that it's actually starting to warm up again, and the temperature would probably be in the range of like 147 Celsius, as best as I can work out. So the first question that you guys need to do is, if this facility completely leaks out, they don't get it stopped, what volume would this volume of natural gas stored at this pressure and this temperature be when it comes out to normal temperatures and pressures? So 1 atmosphere, 25 degrees C. So this is a combined gas law problem for you. Next up, natural gas is mostly methane, CH4. Methane is a way stronger greenhouse gas than just carbon dioxide. So it's 25 times more effective at trapping heat inside our atmosphere than is carbon dioxide. So what I'd like you guys to calculate is how much gas would you have to burn to produce carbon dioxide enough to have the same greenhouse gas effect as this methane. So take your volume of methane that you calculated in the previous problem, multiply that by 25, and that's going to be the volume of carbon dioxide that it would take to have the same heat trapping effect as this methane. Okay, so now to figure out how much gasoline you would have to burn to do that. A good model for gasoline is octane, hence octane ratings when you buy your gasoline. So you'll have your volume of carbon dioxide that you got by multiplying your methane volume by 25. Convert that to moles using PervNert at this pressure and this temperature, and run that in a stoichiometry problem, moles to mass of octane. Now we normally don't buy our gasoline in in mass, we buy it in volume, and here is the density of gasoline. So once you get your mass of octane, you can convert it to what it would be as a volume. Oh, I guess it put the second page of this on another slide. So let's advance a slide to my second set of problems. Okay. A 2-liter tank contains 10 grams of each of these gases. So 10 grams of methanol, 10 grams of carbon monoxide, and 10 grams of hydrogen. What I'd like you guys to do is find the total pressure in the tank. So that's a per inert problem, but you'll need to find the total number of moles. So 10 grams of this is how many moles, 10 grams is how many moles, 10 grams is how many moles. Sum all those up to find your moles and then plug that into per inert. Alright, partial pressure for each gas. Remember that the partial pressure is equal to the pressure of each individual gas over the total pressure, and that is equal to the moles of each individual gas over the moles total. So you should have, at this point in the problem, solved for the total pressure, and you'll know the moles of each and the total moles, and so you can work out the partial pressure of each gas. Okay, I'd like you guys to tell me, this kind of goes to the video that you watched yesterday, how would the average kinetic energies of each gas compare? Take note, everything is at 400 degrees, so everything is at the same temperature. And also referencing yesterday, since everything is at the same temperature, how would the average speed? So that's like thinking back to those Boltzmann's distributions, the peak speed for each gas compares. So you'll base that off of the fact that each of these will have different molar masses. Last question for this one. If we lowered this temperature from 400 degrees to the point where our methanol goes from gas state to a liquid, so we get below the boiling point of methanol, some small amount of the hydrogen gas and the carbon dioxide gas will be dissolved inside the methanol. Which of these gases would you expect to be more soluble in methanol? So you're going to have to think about the intermolecular forces present in methanol and the intermolecular forces present in carbon monoxide and hydrogen, and kind of like solubility in the liquid state, like dissolves like. Polar things are better at dissolving other polar things. Non-polar things are better at dissolving other non-polar things. So if you identify the intermolecular forces in all three of these, you'll be able to say which one should be more soluble. And the last question, we have a tank containing some C2H4, some ethylene, and it is heated from 300 Kelvin to 450 Kelvin, and the pressure is seen to increase. So I want you guys to describe to me, not math-wise, so don't reference like Gay-Lussac's law here and the relationship between pressure and temperature. I want you guys to describe to me what is happening that causes this pressure to increase, like at the molecular level. What are molecules doing as you increase their temperature that would cause them to increase the pressure? So my suggestion to you is think about these molecules flying around, and the pressure is created when they collide with the walls of the container. So what's going to be different about those collisions that's going to cause the pressure to increase? And if you're really good, you can think of two things to say about the collisions. Once the tank has reached 450 degrees Kelvin, they inject some additional gas, some hydrochloride gas, into it, and this reaction occurs. Initially, the pressure increases when they inject the gas, but as the reaction occurs, the pressure decreases. So, again, no math, just describe to me what is happening at the molecular level that explains why you inject the gas, the pressure initially increases, but then the pressure decreases again. All right, so if you've got any questions about this, just post them in the comments section, and I'll be checking on that from time to time throughout the day. And have a great snow day. I expect to be talking to you guys again tomorrow.